Okay, the next video that we'll be doing is for trig derivatives. Again, my name is Mr. Lakin, if you forgot. I'm going to be looking at the derivative of y equals sine x and y equals cosine x. You will need your packet out in order to complete these. I'll be completing them on a separate sheet though. After this, we will go ahead and try the two problems that are given to us, which are these. So we'll do these problems afterwards. Before we start, we're going to need the following information for us. The first one is going to be the limit as h approaches 0 of sine of h over h. We're going to need the limit as h approaches 0 of 1 minus cosine h over h. We're also going to need to know a couple trig formulas, for instance the sine of a plus b, and we will also need one other one, the cosine of a plus b as well. The limit as h approaches 0 of sine h over h. We found that to be 1. This was one of our special trig limits back in Unit 1. Limit as h approaches 0 of 1 minus cosine h over h. That was equal to 0. The sine of quantity a plus b. That was equal to the sine of a times the cosine b plus sine of b cosine a. You may remember this from your trig. And if not, that's what it's equal to. And finally, cosine of quantity a plus b is cosine a cosine b minus sine a sine b. And we'll have to use some of this information at some point in order to derive the derivative of sine x and cosine x. So, the derivative of sine x is equal to the following. We know by the limit definition that the derivative of sine x is going to be equal to the limit as h approaches 0 of sine of x plus h minus sine x, all divided by h. Notice we have sine of x plus h here, that quantity, and we just went over what exactly that quantity is equal to. So let's go and rewrite the limit. We're now going to have the limit as h approaches 0 of sine of x. Remember, x is going to be equal to a, h will be equal to b, and I'm plugging them just into this identity. So we're going to have sine x cosine h plus sine of h cosine x. I'm writing the h in parentheses to show that it's the argument of the function. If I didn't, that's actually another trigonometric function, the hyperbolic cosine function. Please don't worry about that for now. We won't forget about our minus sine x at the end, and everything is divided by h. This first two terms just came from sine of x plus h. Now, we're going to have to do a little bit of some moving around, and we'll need to do the limit as h approaches 0. I notice that I have a sine x over here and a sine x over here, so I'm going to combine those. And I'm going to combine them in such a way that I'll have sine x and I'm going to have cosine h minus 1, because if I distribute sine x back, I'll get sine x cosine h, which was the first term. And then if I distribute sine x to negative 1, that's a minus sine x, which is the last term. For the middle term, I have plus, I'm going to rearrange this, cosine x, sine of h, and then we're dividing this by h. Both quantities are actually divided by h. And we'll put parentheses around the entire argument for the limit. Next, I notice here that I have a sine x, and my limit only involves h. Because sine x is a coefficient here for cosine h minus 1, I don't actually need the sine x, because again, the sine x is not dependent on the h value at all. So what I can do is take sine x out of the limit and get now sine x times the limit as h approaches 0 of cosine h minus 1 over h. I can repeat the same thing for cosine x here. I can now take the cosine x out and keep the limit of sine h divided by h. The limit as h approaches 0 of cosine h minus 1 over h looks very similar to 1 minus cosine h, And in fact, they are almost equal. They are off by a factor of -1. Cosine h is positive for this one. Cosine h up here is negative. Similarly for -1, which means this value is really equal to 0. And I'll show that work to make sure it's clear. This is sine x times, the limit as h approaches 0, of -1 times 1 minus cosine h over h plus the cosine of x. Now this limit we already know. We know this to be equal to 1, so times 1. Finally, this limit is -1 times, that limit as h approaches 0 of 1 minus cosine h over h. That's equal to 0. So we have sine x times the -1 times the 0, which will really be 0. And the moral of this story is the derivative of sine x is equal to cosine x. And I no longer have to ever use a limit definition to show that. I can now automatically say that the derivative of sine of x is equal to cosine x. And you'll want to memorize this. You'll want to put it on a flashcard. And we're going to reference this multiple times throughout the course. Let us repeat this process for cosine x. So the derivative of cosine x. Again, we'll keep in mind that the definition of the derivative here for cosine x would look something like cosine of x plus h minus cosine x, all divided by h. Cosine of x plus h was equal to this identity here, x being a, h being b, so we'll rewrite, and we'll get the limit as h approaches 0, cosine x times cosine h being in parentheses, and then notice that it is the opposite sign, so it's not going to be a plus sign here, it will be a minus sign, minus sine x times sine h, and then we'll have the minus cosine x at the end, and this quantity will all be divided by h. Rearranging the terms the same way I did with cosine x, I notice that cosine x here, I have 2 of them, so I'll take one out, and this is going to give me cosine x times cosine h minus 1 divided by h minus the limit as h approaches 0 of sine x times sine h over h. Well, I'll spare you the work on this one because we already did this part in the last problem. The limit as h approaches 0 of cosine h minus 1 divided by h, this value is equal to 0. So what I really have is cosine x times 0. And then I have minus, again, the sine x has no bearing on the actual limit, so it's going to be minus the sine x times the limit as h approaches 0 of sine h over h is equal to 1. So minus sine x times 1. And the bottom line here is we get negative sine x for the derivative of cosine x. So there are 2 parts you need to know now. The derivative of sine x is equal to cosine x for now and always. And the derivative of cosine x, you think it's equal to sine x, and it is very close to equaling that, but you need the negative coefficient in the front. And now we're ready to try the problems. The derivative of 5 times cosine x, we have 5 times d dx of cosine x. And again, we took the 5 out because this is a constant multiple rule. 5 is a coefficient for cosine x, so it's 10. We don't really need to worry about it for d dx. The derivative of cosine x is negative sine x, so we'll get 5 times negative sine x, which simply is negative 5 sine x. Notice again, I didn't need any limit rules here. I didn't need to put this into the original derivative notation with limits. All I really needed to know was the derivative of cosine x, which is negative sine x. For this one, I will need the sum and difference rule. I'm going to do the derivative of 6x with respect to x plus the derivative of sine x with respect to x. And the derivative of 6x, this is the power rule. This is also a line, and the slope of the tangent line is the slope itself. Long story short, that first value has a quantity of 6. The derivative of sine x we just went over. That is cosine x. And this is our answer. Now the one last thing I want to note is the following. The derivative of sine x equals cosine x. This is really easy to overlook its importance. What this is saying is that on the graph of sine x, if I take any point x, I can automatically find the slope of this tangent line as long as I know the cosine value of it. So for instance, if I have, let's say x is equal to pi over 3, what that actually tells me is that the slope of sine at x equals pi over 3 is the value of cosine of pi over 3. So in other words, the derivative, and this is the notation for it, when x is equal to pi over 3 of sine x, I can find that slope of the tangent line by doing cosine of pi over 3. And if I know my unit circle, cosine of pi over 3 is 1/2, and the slope at x equals pi over 3 on the graph of sine x is equal to 1/2.